FEMA P-1100 has a stipulation where you're supposed to put a shear wall on each end of a cripple wall. Now this sounds very easy, it sounds like a good idea. New construction is designed that way, and but it has some problems from a contractor's point of view, and let me show you what those are. From a contractor's point of view, when he has to move all his equipment in two different places, it costs a lot of money. So let's say he's here and he's got all his bolts and he's bolting everything and he's got all his, his drills and all this equipment he has, drags the plywood in, all that stuff. And let's say the access is over here. So he comes in here, and what he'll normally do is he'll find the one that's the closest to the access where there aren't a bunch of pipes and stuff in the way. And then he'll make his panel as long as he can, as long as required, rather than dragging everything over here and having to do the whole thing all over again. Now, it is a very easy procedure to make it so it does not matter where you put it. So a contractor can go under the house, he can figure out, okay, I need to put in 12 feet here, should I put it on this end, put it that end, am I going to remove plumbing, do I have to remove ducts, find the easiest place to do it, which in turn is the cheapest for him and in turn is the cheapest for the owner. The only thing that needs to be done is to tie the upper top plates together. Right now we're going to look at the method by which FEMA P-1100 addresses breaks or joints in upper top plates. So this right here is a joint. In other words, that's a break where two top plates meet. So this section of top plate is coming on this side, this section of top plate is coming on this side, and that's because lumber sometimes comes in 16 or 20 foot lengths, and if a cripple wall is say 50 feet long, you're going to have a couple pieces with these breaks right here. Now the problem with breaks is this right here. So if you have a cripple wall that's this long, and then over on this one side is the only place you can put a shear wall, and there is a break right here, what happens is all the load goes this way to the left of the break. And when it does so, that load cannot make it back to the shear wall, which is nailed into the upper top plate. And that's why addressing these breaks are so important. Now FEMA P-1100 requires that these straps have a capacity of 725 pounds. And I wonder if that's enough. So let's say this shear wall is supposed to resist 4,000 pounds of force. And the load that's being dragged to it to the left of the break is 6,000 pounds. A 725 pound strap is not going to be sufficient. As we just saw, all the load goes into the upper top plate. So for example, if there were joists here that you could see, all the toenails in the joist would go into the upper top plate. If you put some framing anchors in here, say some L90s, the nails would all go into the upper top plate. So that load would go this way into the upper top plate. So I can't really see a reason to put a strap right here in the lower top plate. I'd like to point out, if we use a steel strap here and perhaps there's another break over here, we won't be able to put in our shear walls because we can't nail into, through the strap. Nor do we want to put the strap over the plywood because then it will put too many nails into the upper top plate and it might split. So let's see what those nails do to make sure that the entire house is connected to our shear wall. So this right here is the floor that you walk around on. And then this is a floor joist that supports the floor. And you see how this floor joist, there's a nail that comes in here and a nail that comes in here. There's a nail that comes in here, and then there's a nail that comes in here. So when the floor tries to move, it goes into that floor joist and into the nails, see the nails right here, which in turn go to the upper top plate. So the upper top plate is going to move that way as the floor goes this way. When it goes that way, it pulls on these nails right here in the upper top plate. When those nails pull this way, they in turn pull down the lower top plate, because you see how the nails come up from the lower top plate into the upper top plate, lower top plate up there. So they're connected. So the nails pull this way, and when they pull this way, they pull on the lower top plate, and then they pull into these nails again on the lower top plate, which are connected to the nails connected to the upper top plate right here. So now it pulls on the upper top plate. which then in turn pull against the nails on top of our shear wall, and then all the force goes into our shear wall, which is right where it belongs. So let's go ahead and look at the big picture on that. So here we have the break in the top plate. This entire, cripple wall and floor and everything is disconnected from our shear wall. So now what we've done is we put a whole bunch of nails on this side of the break, a whole bunch of nails on this side of the break. So when the earthquake force comes this way, it travels, through the nails into the lower top plate, because remember the nails go into the upper and into the lower. So it goes into the nails in the upper top plate. Those in turn are connected to the lower top plate, so then the lower top plate goes this way, comes over to the nails right here. Those nails are connected to the upper top plate right here. So what finally happens is all the force gets pulled on that upper top plate, and this is where all the nails are in the upper top plate. And so all the force is transferred into the shear wall where it belongs. Once we join the top plates together, basically the upper top plate all along here is a solid piece of wood because they've been joined together so strongly. So what that means is wherever you put the shear wall, it will absorb the load no matter where the load comes from. So we can put the shear wall right here in the middle. We can put it right here on the end, or we can put it here on this end, or we can put it on this end and that end if we need to. Again, in seismic retrofit work, the big problem that we always have is access. Not only is it difficult to work in because there's very little clearance, but also there's just all kinds of junk on there that you would not see otherwise. And underneath a house, they don't care what it looks like. They'll throw crap everywhere. They'll put everything on the wall. They put heating ducts along the wall. They put pipes, plumbing. They just put all kinds of junk up there. And from a contractor's point of view, the main thing is you just need to be able to work at one location, and so you don't have to drag your tools around. And at the same location, you put in the bolts because all earthquake load goes into the bolts that are attached to the plywood. And then you do the same for your framing anchors up above. So you can do everything in one spot. Saves a whole lot of time, saves a whole lot of money, and saves the homeowner a lot of money and makes it so the retrofit is more affordable. This detail is interesting because it says here that it should be installed with 9 8-penny nails each side of the joint. And I looked in the Simpson Strong Tie catalog, and it doesn't make any straps that take 10-penny nails. All the nails that are in the straps are 10-penny nails. So someone needs to take a look and see if there's a reduction here, especially in light of the fact that these straps are supposed to resist 725 pounds. So someone needs to check and see if there is a reduction there. Another way to do this is to nail up the plywood and then put a 2x4 on top of the plywood and screw SDS screws through the 2x4 and into the top plate. Now it's very critical to get the lags in the center, so one only needs to snap a chalk line to make sure that happens. Let's see how much capacity we can get out of a 2x4. So here the Simpson catalog tells us that the SDS screw can resist 250 pounds per screw. Now we can take that 250 pounds and we can multiply it times the short-term load multiplier of 1.60. We end up with 400 pounds per screw. Now if we put 10 screws on either side of the 2x4, or rather either side of the brake, we will have a capacity of 4,000 pounds in this 2x4. This is a situation we run into fairly often, and this is a plumbing stack. And what that means, this is either a pipe that has 3 inches or 4 inches in diameter, and see how here it breaks this top plate and it also breaks the lower top plate. So we've got a real problem because sometimes, when they break these out, there'll be 3 inches on this side from the pipe and there'll be 3 inches from this side on the pipe. So the total span here is about 9, maybe 10 inches. And so the problem is that earthquake forces will be pushing this way in compression and also pulling this way in tension. So we need to do something about that. And the easiest way to do it is you simply put in a 2x4, just like we saw before, put lag screws on each side, and now we have a connection that will work both in tension and compression. Here you can see why steel straps might not be the best options in seismic retrofit work. Now, when you drive around and you look at new construction, you'll see these straps on the outside walls. And the reason they're there and the reason they're flat and they're straps is because they need to put in siding, stucco, something like that on the wall. And we can't have a 2x4, obviously, in the way. But for seismic retrofit work, where no one's going to see it, the use of 2x4s often seems like the best option. You can get a much stronger connection, they're easier to install, they're cheaper, and overall a good choice.